Lab 4 for bar magnets. So as an introduction, some key ideas are that we'll be using the Biot-Savart law, which calculates the magnetic field created by a constant electric current, and then the magnetic field of a bar magnet, which calculates the magnitude of magnetic field created by a bar magnet at some distance r away. These are the formulas that correspond to those things. And then for our objective for this lab is to use a magnetometer to find the magnetic moment of a bar magnet, and then to use a GlowScript program to model this interaction, see how it should look and under perfect conditions. And then as an intro to some of our results, so we found that as the distance between the magnet and the magnetometer increased and became very far away, the magnetic field approached zero. And then we also found the magnetic field on axis due to the magnet was twice as strong as the field created perpendicular to the bar magnet. And our observed values and computational values were similar in their findings. So as a model and some assumptions, our system was the magnetometer in this lab, and the surroundings were the bar magnet, the Earth's magnetic field, and everything else that was in the room. One of our assumptions was that we wanted to assume that the only fields acting on the magnetometer were the Earth and the bar magnet. So for the actual experiment, first, we needed to find the magnetometer sensor, and then we wanted to find the distance between the magnet and the sensor that would create a B field equal to x times mu times t, where our values for x were 20, 70, 120, 170, and 220, which we'll see the values for that in the next slide. And then we wanted to repeat finding these values for off-axis to find dperp. So here was our distances that we found for each of these. Where we wanted to get our values. As you can see, it wasn't perfect, but the magnetometer on your phone wasn't the greatest, so we had to estimate a little bit when we were trying to find these values. But then you can see the off-axis fields here at the bottom as well. And you can see we had a slope of negative 2.67, which we would expect because as our distance increases, it should decrease by, our field should decrease by a rate of 1 over r cubed based off of our equation. So for our code on our computational model, first we had to make this function to find the dipole moment. So we found that, and then we had our observation locations that we set. Then over here we had our arrows to represent magnetic fields, which we'll see later on in our conclusions. And then to also visualize the magnetic field at some random location, which happened to be 45 degrees off axis. We made another arrow to do this, and again, we'll see all of this here in a moment. So here was the model we created. Here was that 45 degrees off axis. It points out away. And then here's all of the other magnetic fields around our bar magnet. So as our results, after solving for all of our unknowns, we found that the observed B field was this value right here with a magnitude of 5.6 e to the negative 5, but our computed B field happened to be this vector at the bottom with a magnitude of 3.49 e to the negative 5. So fairly close, but again, there was definitely some differences, which we would expect due to some errors. So for our overview and possible errors, while the model did not perfectly match our observed values, it provided a close estimate of the magnetic field and represented accurately how the Earth's field would interact with a bar magnet on a small scale. Some errors would be non-precise measurements for R surrounding small magnetic fields like different electronic devices, and then the discrepancies in values for the phone readings for the magnetic field. So as a conclusion, some what-if questions. What if we hadn't oriented our experiment to compensate for the magnetic north? If we would have done this, it would have been a little sloppy and we really wouldn't have achieved much because you would have had some directions where the two fields were working together, some where they were opposite, and it wouldn't perfectly line up, so we wouldn't have gained much knowledge from that experiment. And if we stuck two identical magnets together end to end and did the experiment again, we would expect the B fields to be about double, not quite because some of the distances and whatnot would muddle with that, but in theory, it would be about double the magnetic field if we had done this. Thanks.